In this video, I'm going to explain how to formulate inverse exponential and logarithm functions. So a review of what they are: the inverse of a function is when the x and y values reverse roles. As a result, the domain and the range of each function are also reversed. So whenever you graph a function, you're going to notice that the inverse of that function has the domain and the range switched, as you see in this example right here. Inverse functions should have a line of symmetry over the line y equals x. So as you notice, this dashed line is y equals x, and these two functions reflect over that line. That's how you can verify that the answer you got is correct. Whenever you graph the original and the inverse function, they should reflect over this line. Also, logarithm functions are the inverse of an exponential functions. So we talked about how in exponential functions, whenever we have exponential, we end up reversing that to a log of the base that is shown. If not, if the log is just by itself, we have the base of 10. And then if we have natural log ln, the inverse of that will be the e for exponential. So the steps to create inverse functions are the following right here. We're going to replace the f of x with a y. Then we're going to switch y and x in the equation. Then we're going to solve for y. And then at the end, we just finalize the answer with rewriting the equation instead of just y equals into an inverse function of the original. So some examples here of how to convert exponential to logarithm is here. We have the log with base of 5 times 25 equals 2. And these arrows show that when we convert this to exponential, we're going to use the base to the exponent of whatever the log equals. So base of 5 to the exponent of 2, and it's going to equal whatever was here next to the log notation, 25. So this is the correct exponential function form of this logarithm form. If we go backwards instead and you're given the exponential form, you're going to notice the base and then write log, annotate the base, and then you look at whatever exponent you have, and the log equals that exponent. And then this base that was created here is wherever we put this number that exponent exponential expression equaled. So use this as needed to practice inverse on the next examples. So the first example here is the function of 5 to the power of x minus 1 minus 4. So we're going to start by rewriting this into y equals 5x minus 1 minus 4. And then we're going to do the inverse, which means we replace the letters of y. We turn that into an x. And then the 5 to the power of y minus 1. And then minus 4. So after this, we're going to look at the base with the exponent. And our goal is to get this by itself. So that means we need to get rid of the minus 4 by doing the inverse, plus 4 on both sides. Now we have x plus 4 equals 5 to the power of y minus 1. And because now this is isolated, we're going to use log. Log is written, and then we look at the base of 5. That's the log base of 5. Then whatever the exponent is, that's what the log will equal. So y minus 1. And then this space that we created here is where we write x plus 4. X plus 4. That's the argument. We call that argument. So to finalize this, we want to be this equation to have it as y equals by itself, and that minus 1 needs to be canceled. So we're going to add 1 to both sides. It's going to cancel. And this notation plus 1 will be our inverse. So I'm going to write inverse function of f is log 5 x plus 4 plus 1. This is going to be the inverse for that. So we're going to use our graphing calculator to write graph the original function, and then graph our inverse function. And then we're going to write our domain and range for each. And again, we don't have to analyze both graphs. When we find the domain and range for the original, that means the inverse domain and range are the original but switched. So let's go ahead and graph that. So we have 5 to the power of x minus 1 minus 4, and then we have log base of 5 x plus 4 plus 1. And to verify that they reflect on the line of y equals x, I'm going to also add the x. That way we can see how these two reflect on that line. Alright, so to sketch it, we're going to just trace some of these points on the calculator. And then if we can find any whole numbers, that would be great. If not, we can just kind of trace right here a y-intercept of 0, negative 3.8. And then maybe 1.2, negative 2.68 right here. It's just a sketch. So it looks like if we go to the left, it's not going to cross over a negative 4. So the asymptote will be there. I'm just going to create a sketch here that shows that. There's an asymptote right here. And that means that if there's an asymptote for the original here, that means our range is going to be minimum negative 4 all the way to infinity. And our domain is left and right forever, so that's going to be negative infinity, positive infinity. If we switch these, the domain for the inverse will be negative 4, positive infinity, and the range will be negative infinity, positive infinity. So that means that when I graph the inverse function that we created, it's going to reflect this data. Based on this sketch right here, it looks like this graph goes to the left all the way to negative 4. So I'm going to jump to that graph and show you how the x values don't go further than negative 3. So at negative 3.8, 1, 2, 3, that's where it touches the x-axis, and then it just reflects. So negative 3, 1, and it looks like it's gonna touch at 0. So I'm gonna asymptote and then that. And again, it's just a sketch, so it doesn't have to be perfect, but the asymptotes kind of remind you of where those limitations are. Okay, I hope this video explains how to rewrite a function to an inverse and how to analyze it for the domain and range. Please message me if you have any questions. Thank you.